Hi everybody, welcome to episode 2. This is all about atoms and elements. We're going to look at atomic theory, atomic structure, and we're going to do some work with isotopes and ions. So let's jump right in, shall we? Alrighty, I always like to start off looking at atoms and atom theory with the history of atoms, or at least the history of thinking about atoms. And you know, over time, a lot of people have contributed to this idea of an atom, including all these people, and so much more. So this isn't everyone, and I would suggest if you're bored, looking up a couple names can really help a rainy afternoon go by if you're that type of person. So anyway, we are really gonna focus on Thomson, Dalton, Millikan, and Rutherford. So Thomson and Rutherford are on there, but Dalton and Millikan aren't. So yes, we first start off with Dalton and his idea of atoms. These certain species have a consistent mass. He had a couple other theories that were pretty revolutionary to think about, but weren't quite correct. Stuff like he rationalized observations about chemical behavior and gave us like the law of definite and multiple proportions. He said that atoms combine in simple whole number ratios. So that's kind of true. Oh, sorry, I didn't finish my sentence. Atoms combine in simple whole number ratios to form molecules of compounds. And he also theorized that in a chemical reaction, we can't take atoms of one element and change them into atoms of another element. They're just rearranged structurally. And that's pretty true, except for like high energy nuclear processes. So he, this was around 1808 or so. And then we go on to J.J. Thomson, who used the cathode ray to kind of look at the size of particles. And it led to the belief that, you know, these particles were in the cathode ray were charged, and they were a lot smaller than people first thought them to be. If you ever, also, if you're bored, definitely go YouTube some cathode ray stuff, because that stuff looks pretty cool. After Thomson, we go on to Millikan. That's how you spell it, I'm pretty sure. And his oil drop experiment. So pretty much what he did is that he dropped charged, he let charged oil drops suspend in like a magnetic field. You know, in a closed system. And he determined the voltage needed to balance these charge drops against gravity, actually. And from that, we can find, he actually found the charge of an electron, which is pretty darn cool. He found it to be, you know, around negative 1.60 times 10 to the negative 19 coulombs. I will revisit that charge later. So that was pretty cool. Now we have, you know, the charge of an electron, and we have the identity of an electron and some other subatomic particles. And lastly, I'm just going to cover Rutherford, who he's known, well, in this case, for his gold foil experiment, where he pretty much had this half loop almost of gold foil, and there's a slit in it, or slits in them. And in a box, he had these things called alpha particles. So in his box, he had alpha particles, and he shot them at the gold foil, and some of them, you know, went out, and some of them bounced back into the system here. And pretty much what we learned from that is that most atoms have a really dense part of them, but they're mostly just space. Okay, so that was atomic history. So now we're just going to break down atoms. They're made of protons, which I'll designate as P superscript plus, neutrons, which are notated N superscript 0, and electrons, which are notated E superscript minus. And that's pretty much the 3 particles that we'll be working with in this unit. There are some more pretty cool things to look at if you're interested, but for now we're gonna stick with this. So just to let you know, the number of protons equals the atomic number. This is pretty much an element's identity, along with the letters associated with it. If you change the number, if you change the number of protons in a given element, it's going to change to a different element, and therefore it's going to have different physical and chemical properties. So that's pretty important to remember, is that the number of protons equals the atomic number. Alrighty. Along with that, the number of neutrons plus the number of protons equals the atomic mass. Atomic mass is usually given in AMUs, atomic mass units, or it could be also considered in grams per mole. So that's important to know as well. And this is because if you look at all around the given charges and masses of the subatomic particles, protons and neutrons have pretty much have a substantially bigger mass than an electron. An electron is, 9.09 times 10 to the negative 28 grams, or I think 10 to the negative 31 kilograms, to put it in to try and put it in comparison with protons and neutron masses. So it makes sense that the number of neutrons and the number of protons make up the atomic mass, because the electrons barely register on the scale as it is. We will, however, feel more of their presence when we're talking about we feel your presence, sorry, excuse me. We'll feel more of, we'll see more of electrons as we talk about ions and bonding and things like that. Excuse me. Alrighty. So, talking about changes in subatomic particles, when you have a neutral element, so there's a 0 charge, and usually it's notated ZA, where Z is your atomic number, and A is your atomic mass. So with these, when there's a change in, can you see that? Oh, you can't. Okay, good. There's a change in the number of electrons from a neutral atom, that's going to yield an ion, either a cat ion or an anion. What I remember is that cats have paws, and so it's positive. So that helps me, but whatever floats your boat. If there's a change in the number of neutrons, that yields an isotope. That doesn't yield a change in the charge of the atom. If the atom or the element presented is neutral, it's still going to be neutral despite the gain or loss of neutrons. It is, however, going to have a change in charge if there's a change in electrons, but not a change in mass, if that makes sense. So we're going to do some problems with that, some example problems. So natural uranium has 3 isotopes. This is a reference question, so I didn't necessarily write this one, but it is a really good one to use. Alrighty, so natural uranium has 3 isotopes. Uranium-234, which is dictated like that, or written like that, 235, and 238. This is the standard way to write different isotopes of an element. You do the, because there's a change in mass, so you just put the mass and the characters. Okay, so the rest of the question says that all of these are radioactive, but only one fuels nuclear reactors and has an odd number of neutrons. So we know it's radioactive and has an odd number of neutrons. So we want to know which one is it and how many neutrons does it have? How many? Alrighty. So I'm going to take out my handy dandy periodic table and first look and find uranium, which is right here. Boom. And its atomic number is 92. So AN equals 92. Now what I can do is that I can take 234 minus 92, because that's pretty much the atomic mass minus the number of protons, which will hopefully get me the number of neutrons. So 234 minus 92, 235 minus 92, and 238 minus 92. Boom, boom. And with my calculator, I can tell that 235 minus 92 is 143, 238 minus 92 is 146, and 234 minus 92 is 142. 235, uranium-235 is our answer. Alrighty. And that's it. That's all I have for you guys today. Thank you for watching. I'm really grateful that you joined me, I should say. If you have any questions, leave them in the comments, or somehow I'll hopefully find a way to get a system up for you to contact me. Or if you don't want to ask me, you can always ask your professors. So thanks very much, guys, and have a great day.